By the way, do you get a link to the Google Drive video? No, even if you don't, I'm going to put it up on YouTube anyway because that's easier to access. But I was just curious. Aren't you also getting a Google Drive video link? Yes or no?
Sir, I don't remember, but I think we got a mail from you.
Sir, I'm not registered, so I'm not getting any.
No, if you are in, okay, you are not registered for as a member of this particular meeting, but those of you who are in the meeting officially, that is, who have this Google Calendar invite sent to them, they should also get a link to the video. I'm not sure how that works. I think that's how it works. You're also supposed to get a link to the video on the hard drive, on the Google Drive. However, frankly, you didn't get it. No, it doesn't matter because I'm going to put it.
And I didn't get the calendar invite.
No, that's because you are not officially a part of the group, right? Yeah, but those of you who are, you have it. Yeah.
I don't remember any such drive links, sir. Maybe
okay. Anyway, it doesn't matter because accessing the Google Drive link anyway is a pain because it's a big file and the streaming is not that great. And moreover, is a YouTube has the advantage that YouTube also changes the video bandwidth or video quality depending on what kind of link you are on. In Google Drive, of course, you'll have to access the whole big file anyway, so it's perhaps a better idea to keep on accessing the YouTube anyway. So that will take some time. After all, I will have to download this and upload there. But still, in any case, you're listening to this right now, so that's not a problem. Okay, Ite, go ahead. So you are going to give us a proof of Cayley's theorem, right? Yeah.
So can you see my screen? I have shared it.
Yeah, we can, but can you magnify this a bit? I am old, I can't really see that well. Yeah. This is okay, I guess.
Fine?
This is fine.
Okay, so I have written here the proof of Cayley's theorem. So we start with a finite group G, and first we define the set F, which is a set of all bijective functions from G to G, and this set forms a permutation group under the composition of these functions. So this is I have also written a proof like how this forms a group. So if these are the functions in the set F dot is also a bijective function from G to G. So we have closure, and the composition of functions is associated. So we have associativity, and the identity map on G is a member of F, and as F is a bijection on G, F inverse also exists and is a bijection on G. So we have inverse. So what we have basically is F is we have the permutation group, and now we consider a function fgx, which is defined as g star x for all of x in G, and G is some element of G. So by rearrangement theorem, we know that fgx is a permutation on G. So it is a member of F. And this fgx can be defined for all elements of G, just for any arbitrary G. So what we have is a set X, fg for all G in G is a subset of F. So the main problem boils down to showing that this is a subgroup of F.
Okay, just hold on a bit.
Yeah.
It's always a good idea to pause and ask whether everybody is following.
Okay, sir.
Okay.
So
and before that, this you are saying small f small g is a permutation on G. Yeah. That may not be a good thing to say, right? Small f small g is just an element.
Okay,
right?
It is a member of
small f sub G is a member of the permutation group on G. Okay, fine.
Yeah. So
the small f sub G.
Yeah. Does anyone have any problem till now? Like, is this legible and all? And does anyone have any doubt? So I don't think anyone has a doubt. So now we have to prove that X is a subgroup of F. So the first statement we can easily prove is that Fe is the identity, because Fe is E star X, which is the same thing, which gives us the same thing. So it is the identity of the group F, and it belongs in X. And for rest of the properties, we just show this identity, and the rest of the properties will follow. So we first write G star H star X, which all three are elements in G, and now we use the associativity on group G. So we can group this as G star and then H star X, which can be written as this Fg of fhx, which is Fg dot fhx. So it dot the composition function of on F, the group F, capital F. And this can also be written as G star H star X, which is nothing but Fg star H X. So now we have the property Fg star H is equal to Fg dot Fh. So the first implication of this is, which can be easily seen, is that closure on set X, because Fg dot Fh is Fg star H. G star H is a member of G, so it again belongs in X. So we have closure. And from this we can also show the identity also exists in X, because we can easily see for any group element Fg inverse is the identity, and associativity follows from the associativity of the underlying group G. So what we have shown now is that X, the set Fg for all G in G is a subgroup of F. Now only what we have to show that there exists an isomorphism between the group G and the group X, and this can be shown very easily. So first we define a map P from G to X, and it is defined as follows. P of G is defined as FFG for all G and G. And now this map by definition is bijective. So the only problem now left to show is that P is a homomorphism. So we can conclude that P is an isomorphism. So to show that, we compute P of G star H, which is Fg star H, but due to the previous property, we can write it as Fg dot Fh, which can be written as Pg dot Ph, which is a property of homomorphism. So we have shown that P is a homomorphism, but as we defined P as a bijective map, P is also an isomorphism. So thus we have shown that a finite group G is isomorphic to a subgroup, or the subgroup F, which is a permutation group on G.
Okay. So any questions from anybody? But remember, if these are all part of your course and also assessment, by the way. So if you think that this is fine, it's okay. But if you want further clarifications, it's better to ask now. And okay, just one question out of curiosity. Why do you think this is such an important theorem?
This theorem.
Yeah, the Cayley's theorem, why is it very important in the general theory of groups? There, of course, is a kind of question which has many answers and different answers for different people. So let's just try to see whether you can come up with one answer which is sort of reasonable.
It relates any finite group to some subgroup of a standard permutation groups, right? Like it shows a bridge between them.
Yeah, but why is that so nice as a result? You're close, but what that really says is that once you understand the permutation group, you essentially understand everything. Now, the permutation group actually is not studied so often in initial courses of, say, group theory, especially for physicists. But well, if you've seen Young tableaus and stuff like that, they all really owe their origin to the permutation group. You may have seen Young tableaus used in particle physics, and you have seen them in the context of unitary groups and other things. But ultimately, they all really owe their origin to the fact that they essentially help you classify the different representations of the permutation group. We will hopefully get to that near the end of the course. Okay, thank you, Ritik. Okay. Since nobody has any questions, we assume that your work, everybody understood everything that you said. And now, let me start with today's topics. We are still continuing basic. Okay, let me just switch on the light here. This should make it a bit better as far as visibility is concerned. Okay, just tell me, can you see this thing properly? That is what I'm writing. See, if I write something direct, is this properly visible? How many of you can clearly read this?
Sir, it's visible.
Okay. Because as I discovered last day, what I get to see is a mirror reverse version. So since I'm not Da Vinci yet, I can't really read that properly. So I'm assuming everybody can see what is being written here. If you can't at any stage, just tell me. Okay. So first, let's start with a simpler property, a simpler concept, that of direct product. So here G1 and G2 are two groups. And the question is, can I build a bigger group out of them? Well, we can easily do this. And the way to do that is the following. You define the direct product G1 cross G2, whose elements are ordered pairs. As simple as it gets. You just take an element small g1 out of the group capital G1, an element small g2 out of the group capital G2, pair them together, and define a composition rule, of course. The composition rule for the direct product group that we want to define goes like this. G1, if you compose G1, G2 with G1 prime, G2 prime, you simply get G1, G1 prime, comma, G2, G2 prime. That means the elements of the group G1 just compose among themselves. Elements of the group G2 just compose among themselves using the respective group composition rules. So this is really as simple as it gets. You just let G1 do its own thing, capital G1 do its own thing, capital G2 do its own thing, and you're done. Now it seems this is so simple that it seems almost trivial that this has to be a group. But let's just still check that anyway. Closure, there's nothing really to check, right? Because as you can see, that if you take two elements out of G1 cross G2, which are two ordered pairs of elements from G1 and G2 respectively, by this definition of composition, the composed result, of course, is G1, G1 prime, which is an element of capital G1, paired with G2, G2 prime, which is an element of capital G2. So this is an ordered pair, so it definitely belongs to a set G1 direct product G2. Associativity, again, nothing really to check because it follows trivially from the associativity of groups G1 and G2. Okay, I'm not going to write this down because this is essentially just two lines of writing to check this. You have to check for the identity exists, and that's rather simple to figure out. You just take the identities of G1 and G2 respectively, and this gives you the identity, the ordered pair formed by them gives you the rather obviously the identity of G1 cross G2. As you can easily check, if G1 prime and G2 prime were E1 and E2 respectively, then this will be G1 E1, that's G1. This will be G2 E2, that's G2, and you're done. Okay, what about the inverse? That is, does G1 G2's inverse exist for any arbitrary G1 and G2? The answer is it does. Again, rather trivially. You just take G1 inverse and G2 inverse, pair them up. It's rather trivial to see that if you multiply or compose G1, okay, I will use multiply because that's easier to say. Although, of course, all of you know that it's not always multiplication in the standard sense of the word. But if you multiply G1, G2 by G1 inverse, G2 inverse, I get G1, G1 inverse, G2, G2 inverse, that's E1, E2. So you get the identity. So you're done. All the four properties that you need to show for something to be a group. I did not write associativity here. But associativity is trivial from that of G1 and G2. So all four properties done, we have proven that this is a group. So there is nothing really to it as such. However, there are certain interesting results which come about here. One important question could be that if I'm given a group, can I write that as a direct product of its subgroups? Why would you want to do that? Well, that's easy to see. After all, how many elements does G1 cross G2 have? The number of ordered pairs here is simply the number of elements in G1 times the number of elements in G2, right? So it's easy to see that even if we start with two small groups, the direct product can end up being a pretty big group, right? If you have a 3-element group and a 4-element group, the direct product will be a 12-element group, and so on. So, if you understand smaller groups, it's sort of easy to see that in a sense it should be easier to understand smaller groups than larger groups. By the way, that statement is not strictly true, right? Because, for example, you all know this, I hope, that if you have a group of prime order, no matter how big, huge the prime is, you understand the group pretty well, right? Can anybody tell me why?
It's cyclic.
It's cyclic, right? It's an abelian cyclic group. It's that follows trivially as a consequence of Lagrange's theorem and so on. A definition of cyclicity. So, but anyway, suppose you have a group of size order peak of size, which is a direct product of a group of size p and another group of size q, both of which are primes. So you understand the basic individual building blocks much better, and using that, and by realizing that this group can be is a direct product of two smaller groups, can make your life a lot easier. Also, when we look at representation theory later, you will find that finding out the direct product of representations of direct product is simpler, not trivial, but simpler, if you know the representations of the original groups. Okay? So, being able to identify a group as a direct product of its subgroups is pretty handy. But let me just go the other way first. Let me just illustrate that given that you know that G1 and G2 have a direct product of G1 cross G2, you can immediately talk of two subgroups which G1 cross G2 has. Now, question, is G1 a subgroup of G1 cross G2? So what would your answer be? Yes? Is G1 a subgroup?
The G1 cross E2.
Okay, so I think the answer should have been no, but you're going to the next level. The next level is not G1 cross E2. That's, I'm not sure whether that's a legitimate notation. But if you form a group, let's call it G1 tilde, which is defined to be the set of all ordered pairs like this, where G1 comes from capital G1, can easily show that this is isomorphic to G1. That's a trivial result, right? Okay, this is defined as this is isomorphic to. So G1 is isomorphic to G1 tilde, which is just formed by taking elements of G1, pairing them up with the identity. G2 is isomorphic to G2 tilde, which is E1 comma G2, where G2 is taken from capital G2. So these two groups are rather obviously subgroups of G1 cross G2. Of course, you have to prove that, but the proof is sort of trivial. Remember, when you say H is a subgroup of G, it has to be under the same composition rule as in G. So when you take elements of G1 tilde, compose them together, you are actually using the rules for composing elements in direct product space, of the direct product group, which is fine, which works perfectly fine here. But what is perhaps not immediately obvious, but is sort of, is that G1 tilde, which is of course isomorphic to G1, although it's not G1 exactly, but it has exactly the same group structure as this, that this is true. The G1 tilde is a normal subgroup of G1 cross G2. That may not be immediately obvious, but the proof is really rather simple, because if you take an arbitrary element, say G1 prime, G2 prime, from G1 tilde, from capital G, so this belongs to capital G1 cross G2, right, the big group. This is an arbitrary element. Now you take an element from G1 tilde, which is G1 E2, and compose it like this. Now, in order to show that G1 tilde is a normal subgroup of G1 cross G2, what you need to show is that every element of this kind belongs to G1 tilde, right? Is this clear to everybody? Of course, whenever I say if this is this clear to everybody, it really means that if it is not clear to anybody, please speak up. But this is rather easy to see. I'm just jumping a step, but it's easy to see that what this is going to be. This is going to be G1 prime, G1, G1 prime inverse on the first element, and on the second element it will be just G2 prime, E2, G2 prime inverse. And G1 prime, G1 prime, G1, G1 prime inverse is some element of G, capital G1, whatever it is, and what this is always E2. So this belongs to G1 tilde, right? So what this really shows is that if you take an arbitrary element, let's call this element small g anyway, you're taking an arbitrary element of G1 cross G2, and you're forming the set G inverse. Every element of this set belongs to G1 tilde. But is this okay?
Sir, if you can, I can see the bottom of your screen.
Okay, that's a very good point. So how can you see up to this?
Yes.
Okay, so I will remember not to go to the bottom line. But why is that? It should be. Let me just check a bit. Although taking a bit is a bit difficult for me.
Sir, I think it's because of the. So I think it's because
You are
of the
sharing
bottom bar of Google Meet.
Okay, are you seeing you are sharing line, something like that? Okay, anyway, I will try not to go there. But so let me just do something nasty. I'm going to write whatever I wrote there up here. G1, so arbitrary G, G1 tilde, G inverse is a subset of G1 tilde. That's what we proved, right? We proved that if we take an arbitrary element from capital G1 cross G2 and composed every element of G1 tilde, take an arbitrary element of G1 tilde, did G1 tilde, G1 inverse, the resulting thing is in G1 tilde. So that's what we proved. But what we need to show is these two are equal, not just a subset. But lastly, we argued that the moment, because this works for all G, it also works for G inverse. We argued that this actually, the moment you have something like this, that this is a subset, that's enough to show that they are equal. Is everybody with me so far? That is, in order to show that a subset H is a normal subset, all you have to show really is this. G8, G inverse is a subset of H. You don't have to go the whole hog and show that G8, G inverse is equal to H. This, of course, G8, G inverse is equal to H is part of the definition. However, this much is enough. Is it okay with everybody? No doubts, right? Fine. Yeah.
So could you explain why it would be equal, like a bit explicitly? I'm slightly confused about that part.
Okay. So, no, why it should be equal is simple, because it has to be equal according to the definition of the normal subgroup. I guess your question is, if G inverse is a subset of H, how are we so sure that this actually tells you the G8, G inverse? Remember, this is true not for an arbitrary G. If this were true just for a given G, this wouldn't work. But this is for all small g in capital G. If this works for all small g in capital G, then it also works this way. Now, there's something which I was taking for sort of granted, but which we should not really perhaps take for granted, which is this. If the subset A is a subset of B, where A and B are two arbitrary subsets, not even subgroups, GA is a subset of GB. Is that something which is obvious? Remember, what does GA mean? GA means take all the elements of the form GA where A belongs to capital A.
Okay, yeah.
GB where B belongs to capital B. Since every element of A is in B, then every element of GA is in GB. So this thing works. Well, if GA is subset of GB, that also implies A is a subset of B. Is that okay?
Yes, sir.
So in other words, GA G inverse. This of course, if it works only for all G, all of these, this one works for A. Even if you take a particular G, this will work. But if this is true for all G, then you get this. GA G inverse is a subset of H. Fine. Because this is for all G, all small g belonging to capital G. It also works for G inverse. Right?
Yeah.
Because the segment is true for all G. That's what I'm stressing. Just proving this for one particular G will not work. Because we proved that this works for all small g, it also works for G inverse. But then you can hit this with a G on the left hand side and say HG is a subset of GH. Right? Can't you? If this is G here, G composite, G inverse basically will be. You should check whether the algebraic steps are actually correct by writing out the steps explicitly, but the shorthand sort of works. And then H is a subset of GH G inverse. Because I'm just hitting with G inverse on the right, on both. I'm just using the fact that if A is a subset of B, then GA is a subset of GB or AG is a subset of BG. Right? And that's what we are just using here. So what we did, we started with GH G inverse as a subset of H for all G, and we ended up with the statement that H is a subset of GH G inverse, again for all G. That means, of course, H is equal to GH G inverse. Right? This is how you prove two sets are equal. You show that one is a subset of another and vice versa. Is it okay?
Yes, sir.
So, in order to see whether each of these steps actually work, you may have to write out the sets explicitly, but it's sort of a trivial result of inclusion. Okay?
Sir?
Yeah. Yeah, go ahead.
When you said that GA is subset to GB, then you can say A is a subset of B only if it works for all G. Why do you need all G? Like, even if it works for single G, won't that statement be true?
Okay, that's a good question. I may not have been correct about that. Let me just think about it. If G is a subset of GB, then that means GA belongs to GB. That means there exists some B prime belonging to B such that GA is equal to B prime. So A is G inverse B prime. Now, are we sure that G inverse B prime? Okay, so what we have to show is that A is a subset of B, right? That means every element small a is an element of capital B. Every element small a of capital A is an element of capital B. But are we sure that this is an element of capital B?
Sir, but GA should be equal to some GB prime, right? Because GA will be some element in GB.
Okay, that's a good point. GA is equal to GB prime. Right. So you're also right. You're right. I was trying to be extra careful, but this also works. You're right. Even for a single G, this will also work. Because G inverse, of course, can be applied on both sides and you can just cancel out. Good.
Yes, sir.
Thank you. I made a mistake. Okay, I did not make a mistake, right? Okay, I should at least, try to excuse myself by saying that what I said was not wrong, but it was overly careful. Or did I really say that it will not work if it's a single G? I guess I said that. Then that's wrong.
Yes, sir.
But what I needed to emphasize is that since we know everything, one of our results work for all G. Here, of course, we needed to work for all G, right? Because we need also to work for G inverse.
Yes, sir.
For this, the all G part is essential. For this one, it was not. You're right. Okay, so after that fiasco, let's come back and semi-fiasco. Let's come back to G1 cross G2. We've already said that we have two sets, two groups G1 tilde, which, we are going to be sloppy and not distinguish between isomorphic groups. So we often say G1 and G2 are normal subgroups of G1 cross G2. What we really mean is G1 and G2 are isomorphic to groups which are normal subgroups of G1 cross G2. And the isomorphism is another standard trivial one. Okay. And by the way, what is the intersection of G1 and G2? Okay, this is absurd. We are really not like talking of this. We are really talking of this. So let's. What is the isomorphism here? What is the intersection here?
Identity.
Well, the intersection here is E1, E2 because that's the only element which belongs to both G1 tilde and G2 tilde, right? So the reason why I bring this up is the theorem that we have. The theorem is, well, the theorem essentially is the converse of what we have said here, which is let G be a group. Remember the question we were asking is, given a group, can we think of breaking it up into its components in such a way that the group G is a is a direct product of its components? And the ultimate aim of this will be to simplify our study of groups by looking at smaller groups. Suppose we have a group with normal subgroups. Okay, N1 and N2. And we have two results. One of them is N1 intersection N2 is just the identity of the group G. And D is N1, N2. Okay, by the way, what does this mean and how is this different from the direct product? Anybody remember what this means? The theorem is, if this is true, then G is isomorphic to the direct product of N1 cross N2. So what does this mean? When you say multiply two sets, all you mean is you take elements from this set, multiply them together, form a bigger set, right? You're claiming that G is the product of the sets N1 N2, okay? And G is of the and N1 and N2 have this basic form that N1 and N2, they are normal subgroups, so they must have one element in common. The identity has to be there, but that's the only element in common. That's what you're claiming. Okay? So is the precept of the theorem clear to everybody? So we are starting with this thing that G has this particular form, G is N1, N2. That means for all small g belonging to capital G, there must exist N1 belonging to capital N1 and N2 belonging to capital N2 such that okay, is it clear? So next question, are N1 N2 necessarily unique? For a given G, this decomposition that G can be written down as an element of capital N1 times an element of capital N2. That's fine. That might very well happen when you multiply elements of sets. But is this a unique result? That is, given a G, can I uniquely identify the N1 and N2? So let's check. Okay, is the choice of N1 and N2 unique? Of course, unique, I mean unique for a given G. So let's try. Let's say it's not. Then what do you have? You have N1 prime, N2 prime equals N1, N2, right? That means G can be written down in two different ways, let's say, as N1, N2, where N1 and N2 belong to capital N1, capital N2 respectively, and n1 prime, n2 prime. So here we are assuming that n1 and n1 prime both belong to capital N1, n2 and n2 prime both belong to capital N2. So n1 prime inverse n1, if I just move this to this side, it's n2 prime n2 inverse. So can you argue from this that n1 prime has to be equal to n1 and n2 prime has to be equal to n2? Yes? Okay, what does this left hand side belong to? This must belong to n1, right? Is that okay?
Oh, yeah.
What does this belong to? So this element, which is left hand side and right hand side are both equal, this must belong to the intersection of n1 or n2, right? So it belongs to both n1 and n2. But we just argued, or we just assumed that n1 intersection n2 is a singleton set. It has only the identity. That was the precept of our theorem, right? We have two, not only do we have two normal subgroups, these two normal subgroups are special in the sense that their only common element is the one element that has to be a common element, which is the identity. Is that okay? And this obviously means that n1 equals n1 prime, n2 equals n2 prime. So this decomposition is unique. Okay, question. Did we need that n1 and n2 be normal subgroups for this argument to work?
No, sir.
No. What did we really need?
Just the intersection thing.
We actually needed the fact that n1 and n2 were subgroups, right?
Yeah. Oh,
that you needed.
Yeah.
Because otherwise you couldn't have said that this belongs to n1. If you just started with two arbitrary subsets,
Yeah.
that argument would fall flat, right? So this has to be, this is the subgroup property of n1, this is the subgroup property of n2, and the intersection. So this particular result this decomposition is unique would have worked if, say, G were of the form H1, H2 and H1 intersection H2 is just the identity provided H1, H2 are subgroups. Then any G can be uniquely decomposed into this form H1, H2, where H1 and H2 would be uniquely determined by the G. Is it okay? So up to this point, we did not use the fact that n1 and n2 are normal subgroups. Okay? Clear? Okay, now we come to something where the normal subgroup nature will become important. Now this is actually an important, okay, let me just give some general gyan anyway. Whenever you see a mathematical theorem, what you really should do is dissect it thoroughly and understand exactly which part of the conditions that went into the theorem were essential for which part of your result. If your theorem was rigorously properly stated, then all the things that you put in your theorem will be needed somewhere or the other in the proof. Okay? But not all of it may be needed for all of the proof. Right now you can see that for this part of this proof, we just needed the fact that n1 and n2 are subgroups. We did not need the normal nature. And the intersection is identity. Okay? But the fact that now we have a unique decomposition allows you to define a map F from G to N1 cross N2. N1 and N2 are two groups, right? So we can always form the direct product. What is this map? This map takes f of G. It has to map it into an element of N1 cross N2, and G is f of G is uniquely N1 N2, right? So you can say that this map is well defined. The fact that this map is well defined depends on the fact that the decomposition of G into an element of N1 into an element of N2 is unique. Okay? Clear? So what we have to show really is that this F is that the F is a well defined map we have already established. We have to show that F is an isomorphism, and we are done. Okay, so what do we need to show? We need to show that is onto is 1-to-1 and that is a homomorphism. Okay? That is onto. Is that easy to see? Well, that is onto is rather trivial, right? Because how do you show that a map is onto? You say take any element from the codomain and check whether it can be found from some element in the domain. Well, take any element of the codomain N1 cross N2 is of the form of a pair like this. Just multiply the two elements, you get an element in capital G, and if acting on that will give you that. So onto is trivial. How do you show it's 1-to-1? To show that is 1-to-1, you have to show that if f of G is equal to f of G prime, right, then G must be equal to G prime, right? But isn't that sort of obvious? Yeah. Is it obvious or no?
So it relies on the dependence on the uniqueness of making G equal to N1 into N2, right?
Well, not really, in the sense that yeah, G equals N1 N2, and G, if G prime also gives you that, then G prime will also be N1 N2. So G must be equal to G prime, right? So that's sort of, it's even more trivial than the uniqueness actually goes into proving that the map is at all well defined. That given a G can uniquely identify an N1 and N2. And but after that, it's just a matter of the fact that if you multiply two elements, you always get a unique answer. So that's really the group property that we are using here. Okay, but now what we really need to show is that this is a isomorphism. Okay, so suppose G is N1 N2 and G prime is N1 prime N2 prime, two different elements. G and G prime are two different elements. Of course, N1 prime belongs to capital N1, N2 prime belongs to capital N2. Let's consider what f of G prime is. We need to show for this to be, we have already shown that there is a bijection, 1-to-1 onto. So what we need to show really is that this is actually an homomorphism, that f of G prime is f of G prime. So what is this? This is f of N1, N2, N1 prime, N2 prime, right? Now we are stuck a bit because we need to show that this is actually equal to f of G prime. So I'm cheating a bit here. If I wanted to show this, f of G is of course N1 comma N2 and this is N1 prime comma N2 prime. This should be N1 prime comma N2 prime. right? But to say that this is equal to n1 n1 prime comma n2 n2 prime, that doesn't quite look right. If I could make this n1 prime jump across the n2 and come here, then of course I would say the argument of f here is n1 n1 prime, which is an element of capital N1, n2 n2 prime, which is an element of capital N2, and therefore the map must give me n1 n1 prime comma n2 n2 prime. Okay, so the question really is this: I have to show that an arbitrary element of capital N1 commutes with an arbitrary element of capital N2. Notice so far normal subgroups have not been used in the argument anywhere up to this point, except that of course we should have a sneaky suspicion that the normal subgroup should be important somewhere. And where will it be important? It will be important exactly in this part of the proof. If you take an arbitrary group, which if it's abelian, of course there's nothing left to prove here, right? Every element commutes with every element, so I can make everything jump across. But the group that we are talking about is a general group, need not be abelian, right? So what we need to show, and this is where the normal nature of the subgroups N1 and N2 come in, we need to show that any element of capital N1 will actually commute with an element of capital N2. You can show that, then this proof is done. Okay, so pending the proof that elements of capital N1 commute with elements of capital N2, we have proven that this map is a homomorphism. Are you with me so far? Of course, when I say we have proven, I'm really lying, because to prove this we'll have to first establish this result about commutativity. But are you with me so far? That if we could argue somehow that elements of capital N1 must commute with elements of capital N2, then we are done. Is this okay? If this is okay, then let's go ahead and prove that. So the question is, how do you prove that two elements commute in a group A and B? How do you prove A and B commute? Well, of course, what you do is form two elements AB and BA and check whether they're equal, right? If these were matrices, you could say something like, so hold on, I've just got a question now. দেবাশিতা, আমি এটা ক্লাসে আছি, আমি আপনাকে পরে ফোন করছি। আচ্ছা হয়ে গেল। ওকে ওকে, বাই। Sorry about that. Okay, how do I get this to mute? Yeah. Now, if this were matrices or operators, we would have done something like this. Found out the commutator AB minus BA and put it equal to 0. Right? This is called the commutator because it essentially tells you whether the elements commute or not. Of course, the problem is we cannot use this in group theory. Because to use this in group theory, there has to be to use this at all, there has to be an underlying linear space structure. The minus should make sense. In a general group, the only operation you have is composition. You don't have a minus. So this is called the commutator when you have an algebra, which is you have a vector space on which you have a product. But this is not called what is the commutator in a group? Can anybody tell me that? Do you know this? The commutator of two elements A and B, how is that defined? In group theory, not in algebra theory, or not in quantum mechanics the way we deal with it. Of course, in quantum mechanics we deal with it because it's already an algebra made out of the operators. You are being able to add and subtract the operators. But how do you define the commutator in group theory? You have studied this in group theory somewhere, haven't you? Yes or no? If it's no, just tell me.
So you told us that in our course, but I don't
Okay, good.
The computer.
Okay, I keep on forgetting that I actually took your course. Yeah, anybody remembers that?
Should we just? No, I don't remember, but can we just do multiply on both sides by BA inverse, and if they're commutative, then
Okay, you
we
are
should get
exactly in the right track. The commutator of A and B is defined to be AB, A inverse, B inverse, which of course is BA inverse at the back, right?
yeah.
Why do you call this a commutator? Because, well, it tells you whether A and B commutes. If A and B commutes, and only if A and B commutes, this is equal to identity, right? If A and B commutes, it's easy to see that you can make B and A inverse jump across each other, and you get A inverse equals BB inverse. Who is this? Okay. So we have A inverse, BB inverse, and that's identity times identity. So this being equal to the identity tells you that A and B commute, right? Of course, this being equal to identity immediately tells you that AB equals BA, and if A and B commute, it's easy to see that this will come. They will give you the identity. So you don't even have to, by the way, you might say if A and B commute was the guarantee that A commutes with B inverse, or you don't even have to do that, right? Because if A and B commute, you can make these two switch. You get BA. A inverse, of course, gives you identity. So then you get BB inverse, which is identity. Anyway, this is the commutator in group theory. Okay. Now, what I need to show is N1 belonging to capital N1 and N2 belonging to capital N2. These two commute for arbitrary N1, N2 belonging to capital N1 and capital N2. So we form the commutator of N1, N2 and check whether it's the identity. So what is this? N1, N2, N1 inverse, N2 inverse. And we need to show that there is an identity. Now this is exactly where the normal subgroup nature of N1 and N2 come in. And it's easy to see that, right? If you take these two elements, what does this belong to? N2 is an element of capital N2, right? Which is the normal subgroup. N1, N1 inverse do not belong to capital N2, but they are arbitrary elements of capital G. So where does this what does this belong to? There is some element of capital N2, right? Has to be. That's what a normal subgroup is. To do this conjugation operation on an element of a normal subgroup, it stays within that normal subgroup. Now what about this one? What does this belong to? Clear? Because this is an element of capital N2. This one is of course an element of capital N2. The product has to be in capital N2. So in the second step, of course, we just use the fact that capital N2 is a subgroup. But in the first step, we did use the fact that capital N2 is a normal subgroup. This is okay? But now, just look at this. What does this belong to? Right? Because N1 inverse is an element of capital N1. And here you're conjugating that with some element of capital G. And it has to belong to capital N1. And the whole thing has to belong to capital N1. So what about this commutator? What do you know about the commutator? It belongs to capital N1 and it belongs to capital N2. Yeah, Ritik?
Yeah. No, sir, it's identity because it belongs to both.
Right. So it has to be the identity because the only element which is common to capital N1 and capital N2 is the identity. Okay. So notice in this whole proof, there's only one place where you actually had to use the fact that capital N1 and capital N2 are normal subgroups. Otherwise, you didn't have to, right? All the rest of the proof, you did not use the fact that capital N1 and capital N2 are normal subgroups. But this is one place where you needed them. So C N1 N2 is identity, implies N1 N2 equals N2 N1, for all n1 belonging to capital N1 and all n2 belonging to capital N2, which means if we go back to our proof, the one step which was iffy here, f of gg prime of course was f of n1 n2 n1 prime n2 prime, but because we have proven that arbitrary elements of n1 n2 commute, I can make them jump across each other and I get f of n1 n1 prime n2 n2 prime, and then just by appealing to the nature of our map get n1 n1 prime comma n2 n2 prime. So that f of gg prime is equal to f of g prime, which is what we need for f to be a homomorphism, is proven. And because we have already established that f is onto and 1 to 1, we have managed to prove that this is an isomorphism. So the upshot of all this is, if given a group G, we can ever find two subgroups N1 and N2 which are normal, whose intersection is the identity, is just a singleton set with the identity in it, and whose product, as just product of sets, is the group G itself, then G is isomorphic to N1 cross N2. So how do you write a direct group as a direct product of its subgroups? You identify normal subgroups, check whether their product is the identity, also check whether the intersection is the you check whether the product is the group and also check whether the intersection is a singleton set with only the identity in it. Okay. So far, this should be easy. The next group that the next way of forming bigger groups out of smaller groups is called the semi-direct product. The semi-direct product, if you look at its formal definition, it looks pretty messy compared to the absolute simplicity of the direct product proof. The definition. Look at the definition of the direct product. All you are saying is capital G1 does its own thing, capital G2 does its own thing. End of story. Nothing really to be, nothing really complicated about the whole thing. Okay. The only plus point, of course, the plus point of that is you can figure out what a big group does just by knowing what its smaller pieces do. A semi-direct product, if you look at the definition, it looks pretty messy to begin with. So let me just do one thing first. Let's say we want to motivate the semi-direct product. Why would we even worry about semi-direct products? Okay. The answer is there are plenty of situations. Okay, there are two parts to the answer. One is, just like representations of the direct product are easy to figure out once you know the representations of its pieces, even for a semi-direct product of two groups, the same kind of result holds. Not absolutely as simple as in the case of the direct products, but quite simple. So you can build up representations of much bigger groups if you know that it's a semi-direct product of smaller groups. That's one motivation. The other one, which is actually the more important one, is that there are plenty of really important groups which have the semi-direct product structure. So let me just first illustrate an example for you. Now this is an example which most of you would know about. So which group are we talking about here?
Lorentz group.
Sir, the upper part of your page cannot be screen.
Okay, can it be seen now?
Yes, sir.
Okay, so which group is this? Okay,
Lorentz group.
okay, this is really not a group. This is just an element or a transformation. Of course, a set of all such transformations characterized by these matrices lambda mu nu, which obey this particular metric identity. This is a Lorentz group, right? But that's not the group that I'm really talking about. I'm going to talk about this group. Next, this is Lorentz. This again should be something which is familiar to everybody. What group is this?
The Poincare group.
The formal name is the Poincare group. Of course, this really is a combination of the Lorentz transformations and translations,
Yeah.
right? And why are we so interested in this? Because this is a symmetry of almost all physical situations that we can think about. And it's easy to see that it's made up of two very simple pieces, right? Translations in their own right and Lorentz transformations. So in a way, it should be obvious that if we understand translations and if we understand Lorentz transformations, then we understand the Poincare group, right? So an arbitrary element of a Poincare group is really something that represents like this: the Lorentz matrix lambda and the translation 4 vector epsilon. If you know these two things, you know the Poincare transformation, right? So this really, in shorthand, this means that we are talking about the transformation x prime is lambda x plus epsilon. Of course, here x prime stands for the 4 vector with 4 components, lambda stands for the matrix, 4x4 matrix, and epsilon also the 4x1 column vector. Okay. So question is, what is the composition rule here? Say lambda 1 epsilon 1, lambda 2 epsilon 2. This is of course very reminiscent of the direct product nature, right? You are taking an element from the Lorentz group, an element from the translation group, just putting them together as an ordered pair, and you have got an element of the Poincare group, right? So it looks like we are well on track. It looks like Poincare group is a direct product of Lorentz and translation, and that would be nice. That would be wonderful. Because then we have two simpler groups to talk about, in terms of which we can understand the whole group structure of Poincare group. But what is this like? Well, this really means two successive transformations, right? So what we are doing is we are first carrying out x goes over to lambda 2x plus epsilon 2. Thus, we are carrying out this transformation first on x. Then we are going to carry out this transformation, which is we are going to take this 4 vector, whatever that is, multiply by the Lorentz matrix lambda 1. So it's pretty straightforward that this is going to be lambda 1 lambda 2x plus lambda 1 epsilon 2 plus epsilon 1. Okay. So what we have got is this. We have got this result that this product of two Poincare transformations is given by lambda 1 lambda 2, the Lorentz transformation, whatever is sitting in front of x here. Rather nice. We have got the Lorentz transformation structure, right? It's a direct product. So direct product like, at least. But what messes this up is the second term. What is the translation? The translation is not epsilon 1 plus epsilon 2, which would have been the operation in the translation group, right? To compose two translations, do one translation after the other, the next translation is simply epsilon 1 times epsilon 2. Here, that doesn't work. Here you have lambda 1 epsilon 2 plus epsilon 1. It's easy to see why, right? Because you're first translated by epsilon 2, but then you have Lorentz transformed this translated thing, which means lambda 1 gets to act on epsilon 2 as well. And then you are translated by epsilon 1. So the point is, the composition rule for something as simple as this, a Poincare group which has a simple decomposition into a Lorentz transformation and translation, looks similar to a direct product, but doesn't quite work out that way. It's not the translation group and the Lorentz group doing their own things. The Lorentz group very much does its own thing, right? It just gets composed the way Lorentz transformations compose. The Lorentz group part works fine. The translation is actually affected by the Lorentz transformation as well. So notice that this is a tricky situation. You cannot say that you can just think about translations working on their own and Lorentz transformations working on their own. They get mixed up somehow. And this is where the semi-direct product structure of the Poincare group comes in. The Poincare group does not happen to be a direct product of translation and Lorentz. It's a semi-direct product of translation and Lorentz. Do you know of any other example, any other physics example? Okay, just hold on. I will have to connect the charger. My laptop is draining out rapidly. But by the time I come back with the charger, please think about this. Okay, I'm back. I hope I'm still audible. So, if you can hear me, at least let me know.
Yes, sir.
Okay, great. Now, you did have some time to think about this. So, any answers? If not, let me give you a hint. There's at least one more case where you have which you have learned about. You have definitely heard about it, although you may not have looked at it in some great detail. And there, the translation group again plays an important role. What other symmetry do you know about where, okay, it's not really a translation group, but a subset of the translation group plays an important role? Do you remember any physical situation where a subset of translations play an important role? And simpler things than translations in 4 dimensions. These are just simple 3D translations.
So the lattice.
Great. Lattice as a subset of all translations. And what about the symmetries of a lattice? What kind of symmetries does a lattice have?
The lattice discrete symmetry with the lattice vectors.
Okay, discrete translation symmetry with the lattice has. Translation symmetry, of course, is what discrete translation symmetry is what defines a lattice. But you all know that there are different kinds of lattice systems, and they are classified according to their different symmetries. Now, in 3D, of course, you have 3 primitive translation vectors, they define your lattice. So, and that's true for all lattices. So how do you have different symmetry structures? Where do those come from? You have done this in the solid state, right? Yes? You have heard of point groups?
No, sir, it wasn't covered in the
Yes,
course,
sir.
but you introduced us some part of it in your course. Like in the solid state course, the point groups weren't covered. I think the chemistry people did it.
Okay. Okay, anyway, the point groups are of course nothing but symmetries which keep a single point fixed. Could be a lattice point, doesn't have to be, but could be a lattice point. And what you can show is that every symmetry of a lattice can be thought of as a point group operation, which is just rotations and reflections. Some rotations, some reflections. Not all rotations, of course. Some rotations, some reflections. And translations. Every lattice symmetry operation is actually either a rotation or a reflection or a translation or a composition of rotation, reflection, translations. Okay. So what you have is a structure called the point group symmetry, which essentially just looks at, okay, which rules out the translations by this very fact that there is no point which is fixed under translations, right? If you translate, everything moves, every point. So if you rule out the translations, if you are talking about point group symmetries, a symmetry in which one point is fixed, then of course you have ruled out all the translations. So once you forget about all the translations, then you can have rotations about a fixed point, maybe by certain fixed angles. You may have reflection symmetry. You may have combination of rotation reflection symmetry, and so on. These could be symmetries of a particular crystal, and these are called the point group symmetries. But in addition to the point group symmetries, you of course also have the translation symmetries. Yeah.
Sir,
yes.
I just want to clarify what you said. Just to repeat, if I understood correctly. So what you said is, if in any crystal, all the discrete translations can be simulated by rotations and reflections. Is that what you said? Which are point groups, and that's why it's a point group symmetry.
No, I didn't really say that, or maybe I'm hearing you wrong. I said that there are many symmetries possible in a crystal. The most obvious ones which come from the lattice definition itself are the translations. There are discrete translations which are definitely symmetries. But depending on your lattice structure, you may have other symmetries which leave single points fixed.
Oh, okay.
And those are the ones which are definitely not translations, right? Translations move every point.
Oh, okay. Sir. Yes. Sir.
Okay. So non-translation symmetries could also be there. And here the point is, you would have, what are those non-translation symmetries? There would be rotations and reflections. Not all rotations, not all reflections, of course, but specific rotations. If you have a cubical crystal, for example, only certain rotations about certain axes will be symmetries, and so on.
Yes, sir.
Okay, so those are your point group elements. The point group elements are elements of symmetries of the crystal which keep a single point fixed. Then comes the translation. And what about the general symmetry? A general symmetry would usually be a combination of a point group operation and a translation. Okay? Just like the way general Poincare transformation is this is a point group operation in 4D. Can you see that? This leaves one point unchanged. Which is that? You forget about the epsilon mu, just focus on the Lorentz transformation part. There is one point in 4D which stays unchanged. Which point is that?
0, 0, 0.
Yeah, the origin, the origin in time of time and space. 0, 0, 0, 0. That doesn't change under this part. Of course, for a non-trivial translation, no matter what non-trivial translation you're talking about, every point moves, including the origin, right? So this is essentially the same, very similar. In fact, it's rather strange that Poincare is more familiar, perhaps, than the simpler thing, all symmetries of a crystal, which is a point group operation, which will be sitting here. Of course, there is instead of a 4-vector XD, you would have a 3-vector, the point in a lattice, and this would be a 3-dimensional translation, right? That actually is a simpler group than the Poincare group, but it seems to be less known. But you all know its name. If you take the point group and the translations, what you get are all possible symmetries of a lattice, which is called a space group. You know that, you definitely know the terminology, right? You may not know exactly what a space group is. You must have heard of a space group, that crystals are broken up into crystal systems depending on their space group and so on. And the basic thing is, just like the Poincare is a semi-direct product of Lorentz and translation, the space group is a semi-direct product of point group and the lattice translation group. That is a semi-direct product in the very same sense as this one is sort of trivial. The same steps go by. After all, let's just say rotations. You rotate and translate. Then you rotate and translate the result again. The two rotations compose directly on their own, but the translations don't directly compose because the first translation P vector has also been rotated by the second rotation. So here, Just like the first translation vector, which was epsilon 2 by the way, that's the one which got to act first, that got Lorentz transformed by lambda 1 and then got added to epsilon 1. A very similar thing will happen for crystals as well. So it's sort of natural to see that you get something in many cases like this where you don't really have the direct product structure, right? It's not each group on its own, but you have a product structure like this. One group behaves as if it's on its own, the other group gets affected. Is this okay?
Sir, what's the difference between a space group and a point group?
A space group is a subgroup, a space group is a set of all symmetries of a crystal. Okay. A point group is a set of symmetries of a crystal which leaves one point of the crystal fixed. Then, the moment you put in an extra criteria,
so
extra condition,
Lorentz group and Poincare.
It's like the point group is akin to the Lorentz group. Yeah. In 4D, a point group is a Lorentz group, and a space group is a Poincare group. Okay, they're not exactly, is not the right word, but you can see the analogy. Of course, here the translation is not lattice discrete, it's all translations. Similarly, when you go to the 3D Poincare, 3D case for the crystal, of course, you might say the Lorentz group immediately goes over to the orthogonal group. That's the obvious 3D counterpart. But in a crystal, of course, you don't have every element of the orthogonal group as a symmetry, right? A crystal does not stay the same when you rotate by any angle about any axis or reflect about any plane. There are specific reflection, specific rotation symmetries. Okay, so these are, so in a sense, smaller, subset, some subsets, but the analogy is there. Okay, having said all this, so this is the motivation. Why should we bother to study something as complicated as a semi-direct product? And when I say complicated, you must realize that what we have actually said so far, that doesn't sound very complicated, right? So far we have just seen two simple examples where we have two groups which interact with each other. One stays on its own, lambda 1, lambda 2. The other one sort of gets mixed up with the first one. That follows rather simply. In those specific cases, when I say it's complicated, all I mean is if I wanted to define this in general, not with reference to a particular transformation, but just two arbitrary groups, here the definition becomes a bit messier. Okay, first of all, you cannot define semi-direct product for any two groups. Just you could take any two groups out of your bag and define the direct product. The semi-direct product doesn't work that way. The semi-direct product can only be defined. So the defined for and the second group which or actually more in general is isomorphic to okay, this is where my notation becomes horrible. Okay, let's write a curly G and hope can make out that curly G is different from capital G. A subset of the automorphisms of G. Okay, you know what the set of all automorphisms of G is, right?
I don't remember, sir.
Okay. Well, automorphism, an automorphism on capital G is nothing but an isomorphism from capital G to capital G. Right? If two groups are isomorphic, then there should be an isomorphism between them. every group is not trivially isomorphic to itself, right? So there should be many ways of finding an isomorphism between capital G and capital G itself. You can easily show that the collection of all such isomorphisms, G to G isomorphisms, they are actually all what do they call it? They form a group. That's the group odd G. Okay, do I need to prove that for you?
No, sir. It's just a set of functions, right?
These are set of functions which are mapped from G cross G to G.
Isomorphisms between G and G. Okay.
The isomorphisms between G and G, and you can show that they form a group under, of course, the product there, of course, would be function composition, right?
Mm-hmm.
And that they form a group is rather easy to show. That's the group called the Homomorphisms of G.
Yes.
Okay, and written odd G. So what we are saying is we have a group G, and we have a group which is which either is a subgroup of odd G or which is isomorphic to a subgroup of odd G. Okay. Then you can, if this is the case, if you have only when you have this can you define a semi-direct product. Okay. Now I will leave you to ponder about how the Poincare group or how the Lorentzian translation groups fit this picture. But let me just finish, then you should be able to easily see where I am going with this. But let's say we have if we had come to completely arbitrary groups, we could not form their semi-direct product. Okay. One of the groups can be chosen arbitrarily, but the other one has to be either a subgroup of its own automorphisms, or what is more common in application, and it may not be obvious at first sight, but sometimes you should be able to figure out that this works out, that it is isomorphic. The second group is isomorphic to a subgroup of automorphisms of capital G. Okay, so let's start with, forget about the isomorphism right now. Let's say we have taken G and curly G and we are forming their semi-direct product. Okay, semi-direct product needs a name. You cannot write it the same way. Let's put as S here in the middle of the circle. Unfortunately, different authors use very different symbols. So what I'm going to do is I'm just making up one right now. I mistakenly wrote a cross in the circle a while ago, but that of course is a symbol for a direct product. So let's say semi-direct product between these two. How do you define them? Well, this is the group, right? This is what we are trying to define, a new group. Of course, first of all, there has to be an underlying set. And what are the underlying set elements? Are straightforward. Where small g comes from capital G, alpha comes from curly G. So small g is an element of the group, alpha is a automorphism which acts on elements of the group to give you new elements of the group. Okay. So far it's looking the same like the direct product. So what is the difference? The difference is in the composition rule. The automorphisms compose among themselves, alpha prime. Okay. But the original group elements don't directly compose among themselves. Of course, if I want to write a composition rule which makes sense, I can only compose an element of capital G with another element of capital G, right? If I had just said GG prime here, this would have been the direct product composition rule. Okay? The semi-direct product composition rule is simply this. So G is not composed directly with G prime, but alpha, the automorphism, acts on G prime first, produces a new element of capital G, and small g is composed with that. Okay? So there's an intervening step. The automorphism changes G prime. So sort of looks like alpha and alpha prime sort of do their own thing. They're not bothered with the presence of the other group. But capital G does not really behave the same way as it would have under direct product. It doesn't behave independently. When you compose and find out the first element, which is an element of capital G, but the way you do that is you take small g and you take alpha G prime. and you compose them together. But can you see the connection? Lambda 1 alpha epsilon 1, lambda 2 epsilon 2, the Poincare group. Composition rule was this. So can you here identify which one is the group and which one is the group G and which one is the automorphisms? In this case, first, which ones are the
automorphisms?
Okay, but automorphisms of what?
For that, we have to identify the capital G first.
Yeah, but isn't that easy to identify here?
Yeah,
well, there are only two groups involved, right?
Yeah.
Translation and
the Lorentz group.
So notice that Lorentz groups, although we are used to thinking of Lorentz group as own, right? We usually study that before we at all study anything else and so on. But the Lorentz group really, you can also think of the set of Lorentz transformations as automorphisms on translations, right? You take a translation for which is dictated by represented by a 4 vector. You do a Lorentz transformation, you get a new 4 vector, right? Another translation.
Yeah.
So here, in this case, the translation group is our group G. Okay. This group is really automorphism. Is really okay. Isomorphic to a group of subgroup of homomorphisms. Even per group of all automorphisms on the translation group, and when you compose them together in the semi-direct product nature, homomorphisms, there is a Lorentz transformations do their own thing. So of course here in the between the definition of general semi-direct product and our Poincare group elements, we have switched the position. So here the second element really are those for the automorphisms. But you can easily sort of see that. But the group elements, G elements, which are the trans by being mixed up with the automorphisms. Okay, clear? So all I'm trying to do is show you that there is a immediate products don't fall out of the sky; they come out rather naturally, often, and this composition rule for the Poincare obvious, right? And this that you are talking about when you direct products. Composition rule for the semi-direct product is figure out first whether this is a group at all. So G semi-direct product with curly G. Is this a group? Well, of course, when we have to establish that there is a group. First part, just to remind you, this is how the composition rule works. Alpha prime goes its own way, but this is G alpha G prime. Okay. So before G gets to compose with G prime, alpha gets to act on that first. Okay. So this of course belongs to capital G, right? And this belongs to curly G. So no problem. This of course belongs to G semi-direct product curly G. So closure is not an issue. What about the others? Associativity? I will not bother to prove associativity for you, but you can write down the steps and prove it. It's sort of trivial. Well, you have an identity in the group, automorphism, right? One of the automorphisms is the identity automorphism, something which does nothing to your group element. Okay? So this is identity which belongs to the identity of odd G, which is What will I get? I will get E times IG according to the rule and I alpha. I alpha of course is trivially alpha, but IG, and this is important, IG is trivially G, right? That's what the identity operation does. It doesn't change any element. So when you then compose with the identity, you just get G. So this part of the proof, I've just proven left identity. You can also prove the right identity trivial. What about the inverse? Can anybody suggest what the inverse of G, suppose I have a G alpha element, can anybody suggest what the inverse of G alpha will be? Well, what will this element be? That should be obvious. Remember, I should get as a result, I should end up with this, right? So what should this be? This is easy.
Alpha inverse.
This has to be alpha inverse, right? Because they just compose among themselves. However, this element is slightly trickier. What should this element be?
G inverse alpha.
G inverse alpha doesn't even make sense.
Oh, sorry.
Alpha of G inverse.
Sorry, yeah.
Let's see, will that work? If I compose these two, alpha inverse alpha will give you identity, no problem. Okay? But for the first element, what you get is alpha G inverse. If you really did this, you get alpha G inverse composed with alpha inverse G. Right? There's a semi-direct product rule. This first element sits as it is. The second element gets affected by the first element's pair here and then gets to compose. But is this the identity? Or is this G? Is this E? Alpha of G inverse times alpha inverse G? Okay, by the way, remember alpha is an automorphism, which means it's an isomorphism, which also means it's a homomorphism, right? If you are the
So it should be alpha inverse G inverse.
Exactly, should be alpha inverse G inverse. Exactly, because if it's alpha inverse G inverse, then you can use the fact that alpha inverse, the same map is acting on this and you're multiplying them together. So it's alpha inverse G inverse G. Right? Standard rule for homomorphisms. Clear? Alpha, remember, is a member of curly G, and curly G is a subgroup of the group of all automorphisms on capital G. So alpha and alpha inverse, of course, because it's a subgroup, alpha inverse also belongs there. And alpha inverse is a homomorphism, so this works. This is alpha inverse of E. And what is the alpha inverse acting on E? Does it have to be E? If it has to be E, then we are done, right? Then we have proven this first piece. And the second piece was rather trivial. But does this have to be E? Yeah? Come
So
on.
alpha inverse belongs to the set of automorphisms, right?
So alpha inverse is a homomorphism, right? Fine.
Yeah.
So can you prove that any homomorphism acting on E, if F is a homomorphism, Fe is E? Well, that's easy, right? Feg is Fe, Fg.
And FG, yeah. So that has to be.
But this has to be Fg because Eg is G. And since Fg has to be equal to Feg, Fe has to be identity. That's just cancellation law. Fg is an element of the group, of some group. This F could be a homomorphism from G1 to G2 in general. Even for a general homomorphism from G1 to G2, F of E1, there F of E1, where E1 is the identity of G1, is equal to E2, where E2 is the identity of G2. Right? The proof simply goes this way. You take F of E1 times G1 is F of E1 times F of G1, and that's F of G1, and that means F of E1 has to be E2. Cancellation law. And in this case, because it's an automorphism, we are talking of E1 and E2 being the same as E. By the way, we also talked about the isomorphism theorems in the third semester, or fifth semester, sorry, third year course. And there we actually established one very important result. When is a homomorphism? When the kernel of the homomorphism, which is a set of all elements which map onto E, has just this singleton element, the identity itself. Right? The identity element of always belongs to the kernel. But if the kernel happens to be only the identity, the map is an isomorphism. That's what we established. And that's an important theorem. Went on to establish the second isomorphism theorem. What happens when the kernel is not just the identity alone? And then we showed that G quotiented with kernel of the homomorphism is isomorphic to G2. I'm just reminding of these things, maybe we will prove them again if we need them. But just to point out, the reason why I brought this up is this. Here, all we needed was, if you take the identity, map a homomorphism, map it with by an homomorphism, you will get the identity. Homomorphism always semi-direct product. And we are halfway to the direct product is a group, right? What we had to prove was closure, sort of trivial. Associativity, I did not work it out, but it's again trivial from the fact that capital G is a group and odd G also is a group and so on. Identity we just showed. That was sort of easy. Inverse was slightly trickier. You had alpha inverse, G inverse. Instead of alpha inverse was easy. But what exactly is this takes a bit of thought. Not very much, but just a bit of thought. Just to show you that this really works. What about doing it the other way around? Let's say, let's just quickly check. What is this going to be? This is actually even easier to prove because automorphisms do their own thing, no problem. The group element capital G, where the multiplication goes, G comes in, but if alpha inverse G inverse doesn't come in on its own, it's first added upon by alpha. But alpha and alpha inverses are of course inverses, so they cancel each other out. So you just get G acting on G times G inverse, which is of course equal to the identity, and this is of course equal to the identity of the automorphism group, and you're done. So it works the other way as well. Just to point out, can anybody tell me what is this inverse? Lambda epsilon was the inverse of that. Quickly. You should be able to tell me either from your knowledge of the Poincare group or just simply knowledge of basic linear transformations, or you should be able to tell me looking at this. And also remember the notation is sort of inverted. The automorphisms are sitting in the first place here. Lambda is automorphism. So lambda of course goes over to lambda inverse. No problems there. What's the inverse of the what's the inverse translation sitting here? Yeah? What should this be? By the way, what is the inverse of epsilon in the translation group? You translate by epsilon, you just want to invert that.
Minus epsilon. No, sorry. It's minus epsilon.
No, it's not minus epsilon. It's minus lambda inverse epsilon. Look at this. Is lambda inverse acting on minus epsilon? As is lambda inverse is a linear transformation, the minus can come out. Just look at the general result that we had for any semi-direct product. It works this way. And it's easy to understand, right? Because notice that we went to lambda x plus epsilon. You want to invert this. If you invert this by applying lambda inverse first, what do you end up with? You end up with x, that's right, plus lambda inverse epsilon, right? So you want to go to just x, which means you have to add to this a further translation. But that translation is not minus epsilon, it is minus lambda inverse epsilon. So that this piece gets cancelled and you're back to x. Yeah? You do a Poincare transformation, you go from x to here. The inverse must get you back to x. Remember, this is important. The order in which the operations are being done, when you go from x to lambda x plus epsilon, you first apply the Lorentz transformation, then you apply the translation. There's always the rotation, right? When you invert, if you could invert by first applying the translation and then applying the Lorentz transformation, then minus epsilon would have been right. Okay? Clear? Am I making sense here? That is, you can actually think of this as two operations. Right? You understand this? That lambda epsilon, nothing but this. Of course, you can go by the product rule and get that, but it's easier to go just by intuition. What does this mean? It means you just do a Lorentz transformation, don't translate. So you go from x to lambda x. After you do that, and that's very important, after you do that, you do the translation. Okay? So how do you invert? You invert by inverting both, but then the inversion, of course, has to be in the opposite order. Was the inverse of just a Lorentz transformation? It has to be just a Lorentz transformation. Was the inverse of just a translation? It has to be just a translation. But notice that this composition is not. Okay, sorry. This is wrong. This is identity. This is identity Lorentz transformation, I4. Right? If you just do a translation, it means you keep the x the same, you just add an epsilon to it. So this is lambda inverse. And this one is minus lambda inverse epsilon just by the composition rule. You remember it's translation after Lorentz, that's why always that is a convention that you uniformly follow, and that is why the translation that you do in the inverse is not minus epsilon. It's minus lambda inverse epsilon because you have to undo not the epsilon, but what happens after you apply lambda inverse on the result. And that is what this alpha inverse G inverse is doing here. Okay. So a question could be, just like we had in the case of a direct product, this way of finding out whether normal subgroups form of a group G can form G as their direct product or form G as something isomorphic to their direct product. using the theorem, right? If G is equal to N1, N2, and N1 and N2 are normal subgroups with just the identity as singleton element identity as the intersection, then G is isomorphic to N1 direct product with N2. That is actually a very, very useful theorem because it helps you to identify situations where you can write a big group as a direct product of its subgroups and helps you out in simplifying your study of bigger groups. Well, do we have something analogous for semi-direct products? And it so turns out that we do, and there we actually have a result which is even more useful, because in the direct product case you needed both the subgroups to be normal subgroups. Now that's a bit too restrictive, right? Because normal subgroups are rather rare. So being able to write G as a direct product of its two normal subgroups is of course for an arbitrary G. Of course, if you started with G, which is a direct product of two groups, it would end up being the normal direct product of its normal subgroups anyway, right? However, if you started with a G where you did not know anything about about whether it was a direct product or not, and just asked, is it a direct product, you would first have to find two normal subgroups and then go ahead. Well, with the semi-direct product, it so happens that you do need one normal subgroup, and that should be sort of obvious. There's one group which sort of does its own thing, but other group is actually could be a general subgroup, doesn't have to be a normal subgroup. And this is why semi-direct products are more common than direct products. And so in the long run, they end up being more useful. They're a bit more difficult to use, but they are more useful because there are more of them, more examples of them. And I just showed you two very physical examples. So I have run out of time today, especially more so because my wife is going to kick me out of this room soon. Her class is starting in 5 minutes. So I hope all of you are okay with whatever we say today. If not, you can always do one thing. For example, the discussion forum that we have in this thing, you can just ask questions there as well. It's better that you ask questions there so that everybody gets to see. That is, everybody who is enrolled in any one of the PH5102 courses should be able to see that. And I will try to answer some of them there, but we might also discuss them in the next session. So is it okay with everybody? Okay, so I don't have any homework for you today, but okay, not because 1 week may be too little a time, but I would want somebody to talk about space groups and their connection with point groups and the semi-direct product structure. Pocket groups we will handle anyway. Space groups are very important and they are not studied well enough often in a solid state physics course, simply because time is too short. And some of the applications that we will talk will involve crystals, and there the space group structure will be important. So I would ask people to think about whether you want to talk, who would volunteer, of course, to study, to give us an overview of space groups. Okay, so I'm done for the day. If you have any questions, quickly, because I have 2 minutes before I get kicked out. No questions. So, shall we call it a day? Let's stop the recording and bye for today.